Hello, we continue our sessions on Rayleigh Ritz Method. Today I will take up a problem wherein there is a point load acting, but it is acting at a location where the cross section of the bar changes. So the question statement is as follows: compute the value of displacements under given load for system as shown in figure. If you observe the figure, on the left it is a fixed, on the right it is fixed. For a length L1, there is a cross-sectional area A1 and elastic modulus being E1, and then there is a reduction in cross-sectional area for a length L2 until it meets the next fixed end, and its area is A2 and the elastic modulus is E2. The load P is acting exactly at the location where the cross-sectional area changes, and it is an axial load. So in order to solve this, we follow the same procedure as we were doing it before. So the solution, the very first step is to obtain the potential energy function. So potential energy functional is given by pi equals strain energy plus the work potential. So the work potential for bars, we know that strain energy is given by AE by 2, but since we are considering the first cross section wherein A1, E1 and L1 is the length, so it becomes A1 E1 by 2 0 to L1, taking the measurements from left to right. Length at the leftmost end is 0, and for the length L1, the area is A1 and the elastic modulus is E1. Dou U by dou X whole square into dx, plus we have one more bar that we can assume it as a different bar, and its area is A2 and its modulus is E2 divided by 2, and its limits are from L1 to L2. Dou U by dou X whole square dx, and work potential is, it is a point load, hence it will be minus P U1. Therefore, potential energy function of pi, wherein strain energy and work potential, it will become A1 E1 by 2 0 to L1 dou U by dou X whole square dx, plus A2 E2 by 2 L1 to L2 dou U by dou X whole square dx minus P U1. Let me call this as equation 1. The next step is to assume an approximate displacement function, and the question doesn't say anything about the assumption of a polynomial displacement function or a trigonometric, or if it is a polynomial, the first degree or the second degree. So we'll assume, for the simplification of the solution, in order not to complicate the procedure of obtaining the solution, since there is no numerical values involved, we can go with the polynomial approximation for the first degree or single degree. Okay. So assuming or let the approximate displacement function b u equals a naught plus a1 x. I'll call this as equation 2. So this must satisfy the boundary conditions. So applying the boundary conditions, so what are the boundary conditions? At x equals 0, the leftmost end, u is 0. Therefore, if you substitute the values to equation 2, you'll get a naught is 0. Okay. Therefore, equation 2 becomes u equals a1 into x. I'll call this as equation 3. Now I do have the value of u. I need to obtain the value of dou u by dou x. So dou u by dou x will be equal to a1. I'll call this as equation 4. Okay. Now the other boundary condition is at x is equal to L, where L equals L1 plus L2. L1 plus L2, I am naming it as small l. At the rightmost end or right extreme end, displacement u is again 0. Now since on the rightmost end you also have the displacement to be 0, we can take this condition for the assumed polynomial u equals a naught plus a1 into x. But where does this particular boundary condition arise? Now if you look at the equation that we have assumed, it is a single degree polynomial. It is not the second degree polynomial. For a single degree polynomial, if you substitute this boundary condition, this becomes a1 into L, and for that particular a1 into L, a1 becomes 0. So the very purpose why I took this boundary condition is in order to let you know that whenever you are dealing with the first order polynomial approximations, don't try to apply the boundary conditions in an overly manner. Just enough boundary conditions are sufficient. Now if you observe, for the first boundary condition that we have applied, we have obtained u equals a1x, and also dou u by dou x is a1. So dou u by dou x we have obtained. What is the other unknown in the potential energy functional to minimize? It is just u1. So when you are applying the boundary conditions, I know that it will be tempted to apply the fixed boundary conditions, but for the first degree polynomial, there is no such requirement of applying the constraints that are present. So over constraint boundary conditions, it is not required. So this boundary conditions, though I took it in order to explain it to you, if you are going with the second order polynomial, then this boundary condition gets applied. But for the first degree polynomial, this boundary condition is not required. So please bear this in mind. Once you have obtained dou u by dou x, it is only u1 that is pending. You need to apply the boundary conditions in order to obtain u1. Okay. So if you observe, in order to obtain u1, we need to apply the boundary condition at the location where the point load P is acting. Point P is acting at a distance L1. So the boundary condition that we are supposed to apply is at x is equals to L1, u becomes u1. Therefore, u1 is equal to a1 L1 from equation 3. Let me call this as equation 5. Now I have u1, I have dou u by dou x. Now the only thing that remains for me is substituting u1 and dou u by dou x in equation 1, which is the potential energy functional. Therefore, potential energy functional pi becomes a1 E1 by 2, 0 to L1, dou u by dou x is a1, so a1 square dx plus a2 E2 by 2, integral from L1 to L2, dou u by dou x is again a1 square, dou u by dou x whole square into dx minus p into u1 is a1 L1. Now when you apply the integration, pi is equal to a1 E1 by 2 a1 square x from 0 to L1 limits plus a2 E2 by 2 a1 square x from limits L1 to L2 minus p a1 L1. So when you apply the limits, you will obtain a1 E1 by 2 a1 square L1 plus a2 E2 by 2 a1 square L2 minus L1 minus p a1 L1. So this is the potential energy functional. Now once we have the potential energy functional, we need to minimize the potential energy functional with respect to the variable, which is a1. Minimizing the potential energy functional, which is dou pi by dou a1 is equal to 0. So this is the differentiation that we need to make and equate it to 0 to minimize the potential energy functional. Now what is dou pi by dou a1? Dou pi by dou a1 is equal to a1 E1, it was by 2, but since a1 square is present, it becomes 2a1, 2 gets cancelled, so we will be left with L1 a1 plus a2 E2 L2 minus L1 divided by 2 multiplied by the differentiation of a1 square is 2a1, 2 gets cancelled, so we are left with a1 minus p a1 L1, differentiation is p into L1, which is equal to 0, minimizing. So simplifying this, you will obtain a1 as p L1 divided by a1 E1 L1 plus a2 E2 L2 minus L1. So this is the value of a1. Therefore, displacement u1 is given by u1 is equal to a1 into L1. A1 we already know it is p into L1 divided by A1 E1 L1 plus A2 E2 L2 minus L1 multiplied with another L1 will make it P L1 square. So this is the final solution. Since there is no question, the question doesn't state us to obtain the expression in a particular form, we will retain whatever solution that we have obtained, and if there are any numerical values given for the load, length, area and elastic modulus, then we can substitute to obtain the displacement U1 in terms of a numerical value. With this, the set of problems on bars is completed. The next sessions will include Rayleigh Ritz method applied to beams subjected to different types of loads. Thank you.